Hello and welcome to our ME154 project presentation. This is Group 1 consisting of Isabel, Justin, Citlali, and Rafael, and the title of our project is The Manual Brickmaker. So why design a manual brickmaker? One of the main reasons is to accommodate areas with limited access to electricity. In these cases, an automated brickmaker would be less convenient. We also wanted a design that would be cheaper, but still reliable and easily operated by anyone. Some criteria and requirements. For our mechanism, we wanted to go with a crankshaft since that made the most sense for this application. Material-wise, we went with 301 stainless steel. We did research on what other automated or manual brick makers are made of, and steel is one of the most popular. Therefore, that was the material we went with since it's strong and durable. And for our brick constraints, the dimension of our brick is a standard USA size brick, which is 8 by 3 5/8 by 2 1/4 inches. The average weight of the brick is about 4.5 pounds, and we went with clay as our material. Here are our initial design sketches. On the left, we have our first configuration, which has the mold tray and slider at the bottom with the handle on top. And on the right, we have our second configuration with the handle on the bottom and the slider and mold tray on top.
Our original objective was to apply the kinematic synthesis and analysis skills that we have acquired. This took us through a rigorous design process, including the selection of the critical parameters and the primary mechanism. The manual brick making machine comprises of a 4-linkage slider mechanism. The essential parameters include the lengths of the links ranging from 2 inches to 7 inches and a critical angle of 90 degrees. A crucial aspect of our design is the Grashof condition. Our calculations reveal that for the mechanism to operate stably, the angle 2 should be maintained between 10 and 50 degrees. To assess the performance of our manual brick making machine, we conducted position, velocity, and acceleration analysis at point B, just as shown in the MATLAB code here. Considering that we have to press down onto our mold, the velocity and acceleration of our slider are going to be most important components of our mechanism. So we settled on the open configuration due to its practicality and feasibility.
So for our force analysis, we're going to start at our brick in order to find how much force the user needs to put in the handle to make it compress properly. So we found that in order to compress a clay brick, we need a pressure around 2,500 psi. So using this in the area of our brick, we found that force needed to compress the brick would need to be 101.64 pounds at point C. So using this, we're going to find the moment at O, which is basically going to be the torque needed at our crank in that shaft. So after plugging in our angles and then taking into consideration the height, we found that our moment is going to be 15.15 pounds per feet. And then also using this moment, we can find the force that is applied in the crank to be 28.2 pounds. And then going from our crank to our handle, we can find the torque that the user needs to input. And plugging those in, we found the user needs to input 124 pounds per feet of torque. Also looking at the forces in this mechanism of the crank slider, we found that force at OB equals force at BC, and that should be around 101.64 pounds. So going on to static failure, we're going to be looking at the normal bending stress and torsional shear at point A. So for this, our shear stress, we're going to be using the TR over J to find around 11.8 kpsi, and then bending 12.5 kpsi. So plugging this into our equation, we can find max shear and then also solve for our principal stresses. So we found sigma 1 to equal 21 kpsi, sigma 2 equals 0 since we don't have any forces in the y direction, and then sigma 3 to be minus 8480.8 psi. Also, since it's negative, we can tell that it's a compressive strength. And then using these values, we find that our static factor of safety should be 6.8. So now we're going to be looking at our fatigue failure. And then also for our type of steel, we found the ultimate stress to be 200 kpsi and the yield stress to be 165 kpsi. So we're going to find first the coefficients so that we can solve for our stress of endurance. So SE prime we've given from the book. Ka, we use the values also from the book to get 0.806, Kb 0.93, and then Kc under torsion is 0.59. So using this, our stress of endurance is 44.22. Next, we're going to solve for our K of F. And then first we need to solve for Q and KT. And after going through those calculations, we found Kf to be equal to 2.14. So now we can solve for our sigma A and sigma M using those values, and then our F max and F min. F max would be our 101.64 going through the rod, and then our 28.2 pounds needed to compress the brake. So after putting this into the modified Goodman criterion, we found our factor of safety to be 84.16.
When it came to the initial construction of the mechanism on SolidWorks, we had a few prototypes. At first, the design was done to fulfill the mechanism requirement, but did not make sense if used in person. We were also concerned if the mechanism would output or even withstand the force needed to pack and make a brick. The second idea was that we could add another parallel crankshaft on the other side of the machine to compensate. Once constructed, we realized that the handle had to be grafted on both sides of the linkages, making it a two-handed mechanism. It could also constrict the movement of the linkage, and it would end up using more material than it needed. So on the third design, we went back to one linkage and moved it to the center of the press through a connector piece with a handle on the other side. This felt more practical, yet there was an overlooked design flaw. There was a lack of a slider as a guide for the mechanism. From the previous versions, the linkage would have swung over the machine. When concerning the force requirements, we would only need to change the thickness of the linkage or change the material to fulfill the force requirements of pressing the brake, making this design easily modifiable. Now let's look at its motion. For the bill of materials, we only need 8 parts total, 2 bearings for 2 links and the sliding plate, the handle, base, and mold tray.
We worked under the assumption that we are using a homogeneous material, which is the 301 stainless steel, with the objective of compressing a clay brake that typically requires a pressure of 25 psi. With the given pressure, we computed the necessary force of 28.2 pounds through the crankshaft. Additionally, our machine will need a torque of 124 pounds per feet to accomplish this task effectively. The good thing about using this steel is that our machine's construction and its strength and durability. Given our calculations, the force and torque requirements are well within the material's capacity, ensuring a safe mechanism. But here's where things got a little bit interesting. Our calculated safety factor came out to be 89, which realistically speaking is usually high. So this made us re-evaluate. We have identified potential reasons for this anomaly. The first of of them is the overestimation of our steel strength. So we could downgrade to a lower strength steel, and this will ensure a most cost-efficient machine. Another possibility is some calculation errors, which we have found, and also the misinterpretation of the loading conditions. We could have been that we suggested that the entire load might not be shared onto multiple components. We just focused on the crankshaft. While our findings are enlightening, we acknowledge our oversight, and we're actively reanalyzing our work, and we're presenting some improvements in the results. However, we still need to do a second detailed analysis of our design mechanism, and perhaps using a different approach. Our commitment is to accuracy, safety, and functionality. Thank you so much for your time.